Good morning, good afternoon, good evening, wherever you are, everyone. Thanks for joining our webinar today on assessing nutrient loadings in water bodies from reclaimed water practices. My name is Ryan Murdall. I'm the marketing director for Stantec's water team. I'll be your moderator today. Just a few quick housekeeping items, then I'll turn it over to Joan to start the presentation. You will be muted during the presentation. You can ask questions using the GoToWebinar questions function. I will read those at the end of the presentation. Feel free to put those in there as Joan is speaking, as you think of them, and I'll get to them at the end. I will also give you the ability to unmute yourself with 5 or 10 minutes left in the presentation if you would like to comment or ask a question directly or have some discussion. That's great. You will receive a link to the recording from GoToWebinar after the session. We also post all of our recordings from all of our webinars on stantec.com. I will put the link to that website in the chat. And you'll also get a certificate of attendance, so you can submit this to your professional development registration organization to try to get some PDH credit. So with that, I will turn over to Joan, who's a principal scientist in our water applied research team, and she will talk about the subject today.
Thank you very much, Ryan. And thank you everyone for joining the Stantec webinar series on assessing nutrient loading into water bodies from reclaimed water practices. Many of you probably already know me. I'm Joan Oppenheimer. I am a Stantec Vice President and Principal Scientist. I've been working in this field for over 40 years. And I basically focus in the intersection of water quality issues and environmental processes for testing and providing treatment solutions to those water quality issues. So in terms of the background for why we were looking into this, we all know that due to climate change and urbanization and shifting demographics, that there's greater and greater need to use reclaimed water to support water portfolios all over the country. Florida is the water reuse, champion with 820 MGD reported as their most recent number. California doesn't fall far behind with 640 MGD. Reclaimed water use is just expected to increase with time, and it is practiced over a wide part of the United States. And while it is tremendously beneficial for enhancing the water portfolio, it does have sort of an underbelly in the sense that even very well treated wastewater still will contain some level of nutrients, and there are many impaired surface waters and groundwaters as well that could have nutrient impairments, and it's really not well understood to what extent does irrigation with reclaimed water really contribute toward nutrient impairment of listed water bodies, both surface or groundwater bodies. So what we were really trying to do here is develop some kind of a chemical marker that could distinguish loading from reclaimed irrigation water rather than other nutrient-laden sources, whether those be stormwater runoff or leaking septic systems or other unknown sources to the environment. Of course, when a water body is listed as being impaired for a pollutant, in this case we're focused on nutrients, you really have to figure out what's the assimilative capacity of that water body for that pollutant, and you want to make sure that the collective loading that goes into that water body will now never exceed that assimilative capacity. And this is basically done through some kind of an action plan, like a best management action plan. They may be called different things in different states, but it's basically the roadmap for figuring out who is contributing and what kind of best management practices, mitigation measures need to go into place to keep that collective load below the assimilative load. And just as you can see from this depiction of a watershed boundary on the right, source load assignment is really complicated. And this is really always the difficult part in completing an action plan for a TMDL. Another way of looking at it is once a water is impaired, it gets put on a 303D. This is the TMDL list, and there can be a whole variety of nutrient sources that have contributed to that water body being listed. Stormwater, reclaimed water use, septic effluents, wastewater treatment plant effluents, air deposition, fertilizers, etc. And so once something's on that list, a total maximum daily load is created, but then you basically need to get the identified nutrient sources collectively contributing to be below that assimilative capacity, and that plan is then laid out in your action plan. And so we were really trying to insert here and come up with some kind of a tool to help in that source contribution. We called it the Wrf Nutrient Tool because this work started as a Water Reuse Research Foundation grant, and of course, as we gone into subsequent projects, it's now all under the guidance of the Water Research Foundation, where all of these foundations reside at the present time. So we really have a couple of objectives here in this presentation. We did 3 sequential projects funded by the Water Research Foundation to try to identify this nutrient-specific marker for recycled water. So I'd like to just summarize the outcomes of the past 2 studies and present the soon-to-be completed work on the 3rd project that was funded. A lot of this work was done in Florida, but I really want to emphasize that what was being developed here could be applied anywhere. There's nothing specific to Florida in the approach that was developed, but they, as reuse leaders, had tremendous interest in supporting the research. And here you can just see that these are some of the water facilities and regulatory bodies that were involved, as well as the Water Research Foundation. In our very first study, we were really trying to first look at sucralose as a human wastewater indicator. Sucralose, most of you know this is Splenda in the yellow packages, is basically just sucrose where 3 of the hydroxyl molecules are replaced with chlorides. And this molecule is really not broken down. It exists in the environment. And at this point, there's been a lot of work looking at sucralose as a tracer compound. We published a number of papers on use of sucralose as an indicator of wastewater influences and as an attempt to try to differentiate wastewater from septic influence. And these are just listed up here. These were some peer-reviewed publications that came out. And when we took an initial look at reuse water and septic systems and fertilizer and such other sources, what we saw right away was that sucralose is a great wastewater marker, but it can't distinguish between reuse water and septic. And something like galaxolide, which is a fragrance, a musk fragrance that's put into a lot of personal care products, behaves similarly, that you'll find both of these in reuse water all the time, and you'll find it all the time in septic as well. So we immediately eliminated those. We were looking at other compounds that are commonly found in reuse water, like carbamazepine, which is a mood stabilizer, atenolol, which is a heart medication, iohexol and gadolinium anomaly, which are diagnostic tracers that are used for medical imaging. And we saw right away that these diagnostic tracers might have a lot of potential because they're really not found in septic systems because they are out of the body very quickly. They have very short half-life, and so they're not going to be in common use in homes as things like atenolol, carbamazepine might be as prescription medications. What we found with the gadolinium anomaly was that we were running into sensitivity issues because we weren't finding all that much of it in the reuse water relative to the reporting limit of the methodology. So we tried doing some ratios of gadolinium anomaly to the sucralose just to see if that would help us get around some of the sensitivity problems. And what we did notice is that when we consider gadolinium anomaly versus sucralose for sources and field locations, that it was able to effectively label different types of samples. So things that had a heavy reuse input would show up in the upper right quadrant of this graphic in front of you, while things that were much more predominantly septic influenced, or at least, you know, not reuse influenced, would show up more on the bottom. But the big question was, you know, could we just measure these ratios out in the environment and be able to get some sort of semi-quantitative sense of loading? And you really run into, anytime you use ratios, you're not finding anything that's truly unique to the one source you're trying to track. And it's the same problem you run into when you try to use stable isotopes, which we also looked at in this initial project. We looked at stable isotopes for both nitrogen and for carbon. We thought carbon 12 and 13 might work because we eat so much corn-based food in this country that we have a skewed signature of carbon 13 to carbon 12. But really, stable isotopes are just looking at ratios, and when you have mixing from multiple sources and blending of those different ratios, it becomes very difficult to really figure out what's going on. So if you just look at any sort of neat sort of water sample, if you are just given a water sample that is from a pure source, you could use this to get a differentiation. But when you go out into the environment with a mixing scenario from multiple sources, then you just get a blending and it becomes very difficult. And so we sort of had the same problem trying to use this ratio with sucralose and gadolinium anomaly. So we moved into a second study, and we're still trying to develop a unique chemical marker for reuse. And so we were now getting into expanding the analytical methodology. So we weren't just going to do a target list of, say, 98 compounds, but we were going to start doing a non-target list as well to see if something would show up. And we were hoping that maybe we would find some non-targeted compound that would be specific to the reuse, either because, you know, there's just something different in wastewater reuse that's not present in the other sources, but that seemed unlikely. The other possibility was that there might be a treatment difference where maybe you form different parent metabolite ratios or unique disinfection byproducts, because septic is typically not disinfected with chlorine. And so we were just trying to see if we could find something. The source difference would be maybe only just a contrast media or something that is not really in common use in the home. And obviously, whatever we did find would have to be persistent and at adequate concentration, and we would have to understand its environmental fate if it wasn't inert as it traveled in the environment. And so for the second study, Florida actually, DEP actually gave us a BMAP study site location to focus on. And That was the Gordon River extension, Collier County, Florida. This is basically a watershed that is in the city of Naples in Florida. This is the Gordon River extension, and it is impaired for dissolved oxygen, which is attributed to nitrogen levels being too high, and it has an assimilative load concentration based and set to 0.74 milligram per liter of total nitrogen. Now in Collier County, the blue outline is just showing you the watershed boundary. What you do notice is a lot of yellow dots in this figure, and those are their best estimate of where they think septic systems are. And if you get maps from the county versus the state, the dots, the numbers don't add up and the positions don't quite add up. So they're not 100% sure they have all of them, but there is still a lot of septic influence in this area. There's a lot of reclaimed irrigation usage, and they have a lot of golf courses. It's the city of Naples. And 40% of the golf courses lie in the vicinity of the Gordon River. And the Gordon River actually runs right through the middle of this largest golf course that's depicted here. It's hard to see, but it's over where those trees are running from left to right in the middle of that golf course. This is the City of Naples Reclamation Facility. It's 10 MGD AWT facility. It has very good nutrient removal because of a 4-stage Bark-Denfo treatment system. And there's 30 miles of distribution pipes that supply the golf courses, parks, roadway medians, residential landscaping. So I had mentioned that we were going into this project trying to look beyond target compounds that might differentiate reuse. So in addition to just using conventional liquid chromatography, tandem mass spectrometry, we also used high resolution liquid chromatography mass spectrometry. And we were trying to see if we could find any unique DBPs formed from the chlorination process in the wastewater, unique metabolites from the ammonia oxygenase in the secondary treatment, or likewise dehalogenated metabolites from the anoxic phase of the secondary treatment. The 98 compounds you see here, that's what we would normally get from a target compound analysis. With high resolution atomic mass, you can obviously look for thousands and thousands of compounds. The difficulty is in getting an identification. You get tentative library matches. You would have to run an actual standard to confirm what you think you're seeing. And these here on the right list the compounds that we tentatively identified. And one of the difficulties we saw right away is that a large majority of these compounds were herbicides, pesticides, and insecticides, and therefore they would be just as likely to be highly prevalent in stormwater runoff, and didn't seem like anything that would be specific to reuse. There are a few drugs in here, but they all looked like the types of things that would be used by the population. You would run into the same problem of it not being able to differentiate between septic and reuse. We did see imidacloprid, which is a neonicotinoid pesticide, the one that's implicated for killing bees. We did see a breakdown product from it. You see on the left 6-chloronicotinic acid. And we thought, oh, perhaps this breakdown product is occurring because of the reuse treatment, because we didn't see it in other samples that weren't reuse. But the concentration was extremely low, and we knew we'd run into sensitivity problems. So at that point, we decided to go back and look at iohexol, because we knew that wouldn't be an issue with septic. It's one of those medical diagnostics, but we'd had sensitivity problems with the gadolinium anomaly. So in this particular Gordon River location, we went and looked at how much iohexol was in the city of Naples effluent. And we sampled during wet and dry season. So July, clearly wet season, February, dry season, October, sort of on the cusp, and it was more dry season for that particular year. And what we did see was that there was a lot of iohexol in this effluent, particularly during the dry season. We'd be up, at about 10,000. And so we would have a good 3 orders of magnitude of dilution and then still be able to see it because of the analytical reporting limit. So we decided to explore iohexol in the second study. And here, this is just showing you how the iohexol is showing up at pretty high levels at both before and after chlorination in the reuse effluent. We can see it in the Gordon River extension. It's still detectable. We don't detect it in septic, and we don't detect it in rainfall. So we're trying then to go further with the iohexol as a field marker to discern source load impacts. So this was really a proof of concept study. So we just went about this very conceptually. If we measure this marker in the water body of interest, and of course we are measuring this marker in all the other possible loading sources, we could do a simple mass balance in terms of concentration and flows in and out of that river to understand the mass load. But what we'd have to overlay is any transport attenuation going on. And unfortunately, iohexol is susceptible to photodegradation and some biodegradation. It doesn't seem to be an absorbable compound, which makes sense based on its chemical structure. It's pretty much non-ionic. And so we went about trying to figure out the fate and transport characteristics of iohexol. We did some bench scale column studies, and we differentiated between absorption and biodegradation by running one column with study site soil and the second column with that same soil, but we autoclaved the soil. And we did look at 2 different soils in the vicinity of the river, and because not all soils will necessarily behave the same way. And what we did see was there doesn't seem to be much absorption loss. You can get some biodegradation through the soil, and the biggest loss seems to come from photolysis, where if this water is exposed to sunlight for more than, say, a day, you can lose 50 to 60% of it. So we went ahead to do this mass balance. And of course, the beauty of this is with the iohexol only being present in the reuse water, which we've labeled as RW, then basically most of these other terms will drop out because the concentration will be 0 for the iohexol. And so if you just go through the mass balance, you end up with, on the bottom, this fractional flow of reuse to the total flow. So it's just the concentration of iohexol in the river divided by the concentration of iohexol in the river minus the concentration in the reuse water. And so we went ahead and tried to make an estimate of what we thought the volumetric loading was into the river. We did do photolysis experiments to come up with a photolysis constant, which was 0.4 inverse days. Because we truly didn't know what is the exposure time of the water, we just did the calculations assuming a range of times from 0.3 to 2. This would capture any exposure during storage or during if there was an overwatering situation on the golf courses. And if it was reaching the river through overland flow, it was just meant to capture that exposure. We pretty much in this study did not focus on what would be the soil infiltration input to the river. And so ignoring that, we were able to show that this fractional volumetric load would be anywhere from 0.5 to 7.5% for any type of surface runoff if there was, say, a overwatering type of effect going on. And then knowing how much concentrations were in this treated water, if we looked at the nitrate, we would see this is the amount of nitrate that would be contributed to the river and what that was in terms of the total nitrogen limit. So the third study, we were trying to see if we could expand this approach to other areas. And so we had 4 additional study sites, and we were really trying to see what are sort of minimum criteria for someone to consider trying to use this. And really the consideration is when you're a utility that is suddenly going to be hit with a much stricter nutrient permit requirement to get even lower than your current discharge because of an impaired water body, and you really want more empirical evidence supporting whether you really have to do a large investment in treatment at much higher energy input and expense to get your discharge levels even lower if they're already pretty low and you're sort of almost approaching the limit of technology as to how low you can get that value, then it might be worthwhile to try to generate this type of data. So we were really trying to expand to some other study areas and try to see what are some of the limitations that would define areas where it would be difficult to apply, and develop this into a guidance manual that contained these minimum criteria. And then what would be the sequential approach for providing the site application. So we came up with a number of minimum site application criteria from doing this third project. Relative to the wastewater treatment facility criteria, the first one's somewhat, I guess, intuitively obvious, but you have to have reuse effluent from urbanized regions with hospital and diagnostic centers. But sometimes in urbanized regions, they may have multiple treatment facilities, and it may be that the hospital diagnostic waste predominantly goes to 1 or 2 of those and not the others. So just being in an urban region isn't really sufficient. If you have multiple plants, you really would have to do a measurement to see, do I actually have adequate amount of iohexol, unless you really understood exactly how much loading you were getting from these hospital and diagnostic centers through your pretreatment program. Secondly, even when you have enough iohexol, you obviously have to get some understanding of its loading to the environment. In other words, how is it changing in your effluent, both as a result of the diurnal curve, but also is there a weekly distribution? You tend to not see much of this, say, Monday morning relative to Wednesday morning, because a lot of these facilities might not operate over the weekend. So you basically have to collect enough samples to get a statistical characterization, which is what you always have to do with wastewater effluent or influent when you're designing the plant. You have to understand the water quality variations. And then if the reuse effluent is disinfected with chlorine rather than UV, because it's susceptible to photolysis, the UV process itself will dissipate a lot of the iohexol. It's actually being turned into degradates, but if you're just measuring iohexol, that parent compound is going to be greatly diminished. And so we found with UV facilities, unless you have extremely high levels to start out with, you might not be able to utilize this approach. In terms of the reuse storage facility criteria, a lot of times this reuse water might be stored in open ponds, and so it can be susceptible to photolysis. And then, it just becomes a question of how frequently is reuse effluent loading to this storage pond relative to the rate at which the water is withdrawn and used. But if you end up with a situation where it's loaded and not consistently used and it stores in there for many, many days, and then again, it depends on the depth and the sunlight penetration and such, but you may have a situation where you're susceptible to too much photolysis because of the manner in which the reuse effluent is stored. Obviously, if it's stored in a covered facility, it's a different situation, or if it's continually withdrawn at almost the same rate at which it's filled, that's a different situation that might work. Also, sometimes storage is actually consisting of a blend from several service facilities, and if that is the case, you really have to understand the wastewater treatment facility criteria for everything that is going into that storage facility. So, sometimes you may have 2 or 3 different wastewater facilities that are all putting their reuse water into the same pond. That obviously is a complicating factor. And then you have to verify is there a liner used for the ponds? Is the pond itself an actual infiltration point for the effluent that could be impacting the receiving water of concern? And then finally, the transport characterization criteria. We did measure the photolysis rate again in the third project. We did it at a different location from what we had measured in the second project. We got a pretty consistent photolysis rate. And so we do feel that we have some understanding of that photolysis rate, that could be utilized as a good starting point. All you really have to understand is what's the exposure time, and that's based on the manner in which the reuse water may be stored in an open pond, and whether you suspect any overland flow and any transport time for that. If there's no overland flow and there's no exposure during storage, then photolysis rate may not be an issue. But if it is an issue, you can start with that initial characterization rate, and it's probably not a bad starting point. You can always do the measurements again, but as I said, we were able to replicate it. And then you have to verify that you have site conditions that support slow iohexol biodegradation relative to denitrification through soil transport. And this is probably, I would say, the remaining area of this project that requires more research at this point. If your reuse irrigation is largely impacting your water body solely through soil transport, and when we studied this, we didn't really do enough work to be able to characterize what might be going on at other sites. We did see 90% reduction of nitrate and about 30% reduction of iohexol when we just did our soil column experiments without adding carbon to try to drive denitrification. And we probably had oxygen in those columns because, you know, we weren't running this under really sealed conditions, try to prevent any oxygen from coming in. But we really didn't do enough characterization work. If you were trying to say build a model, a global model to understand how this works, we really didn't do enough characterization work to understand the iohexol degradation or dissipation is a better word, relative to the nitrate dissipation. And we did see, obviously, when you have denitrification conditions, you'll eliminate all of the nitrate and you will have very little reduction of the iohexol. But I would say the soil transport characterization is the area that remains that requires some additional characterization, or if someone wanted to do this site specifically, that would be an area where they would have to collect some samples to get a better understanding of that. We also, in this third project, tried to put together a flow chart for how you would go about this application criteria in a step-by-step sequential manner. And we also showed this generically as to how you would proceed going through the application criteria, and then we had an example or two of how we applied it at study sites that we looked at. So to wrap this up, our overall findings was that using iohexol was definitely an improvement upon trying to do gadolinium sucralose ratio for distinguishing septic from wastewater nutrient loading. So iohexol is a much better diagnostic contrast media to focus on than the gadolinium, at least for all of the study areas that we looked at. Iohexol seems to be commonly utilized for this type of imaging. And an approach has been proposed for quantitatively assessing nitrogen-based nutrient loading attributable to reuse practices. And this third study that we just completed defines the minimum applicability criteria, the application approach, and remaining knowledge gaps. Obviously, if those remaining knowledge gaps could be filled, enough data could be generated, it might ultimately possible to try to start generating a modeling approach to try to be able to go to any site and then just collect samples, get the sufficient required amount of data needed as input variables, so then be able to put those into the model and come up with output estimates of what the fractional loading might be. So we do need a better understanding of iohexol degradation pathways, photolysis and the biodegradation during the transport to impacted waters. And perhaps we can do further work on iohexol degradates. We did look at that a little bit in the third project. We had hoped, we did have one UV disinfected plant, and we had hoped perhaps we could find a unique photolysis degradate that was formed in that plant. But that plant, unfortunately, didn't have that much iohexol to begin with. It was a plant in an urban area where most of the hospital and diagnostics seemed to be going to some of their other facilities. Plus they had UV, which dissipated even further. So we were not really able to find anything unique, but we just took a very cursory look at this. And the iohexol degradates there's a lot of complex pathways and a lot more work I think needs to be done to get a better understanding. There are photolysis degradates, there are microbial degradates, and with more research, those might be ways to better understand transformations during the environmental pathways to the impacted water. So that is pretty much a kind of a nutshell summary of what we've been doing on these projects. And so with that, I'll open it up if there are any questions. And thank you for attending.
Yes, thank you, Joan. Very good. A little bit over my head in spots, but I think I got the gist. I'm going to apologize. There's a guy outside my window here with a leaf blower, so it might get a little noisy, but we do have a few questions that have come in. And again, please feel free to use the questions chat box if you have some of your own, and I'll let you unmute yourself here in a few minutes if you'd like to comment. We're going to start off with a technical one that I would not have thought of, but someone did. If you have enough gadolinium in your source water, could that be used instead of iohexol for nutrient determination from septic versus reuse?
Sure. Our biggest problem in trying to use the gadolinium was a sensitivity issue. Gadolinium is actually not an LCMS analyte. It's done like a metal, so it's inductively coupled plasma analysis. So it's a different analytical technique. So that's one thing to keep in mind. And we just didn't get the sensitivity that we needed. There just wasn't that much of that particular contrast agent in the effluent. Now, I imagine this could differ from one location to another, but they don't use these diagnostics interchangeably. They're used, for different types of screening tests. And I suspect that iohexol is much more prevalently used than gadolinium anomaly. I think that it's gadolinium. It's not gadolinium anomaly. The way it's analyzed is through its anomaly in the rare earth series. And I won't get into all of that, but I do think that the gadolinium is used in more specialized MRI diagnostic work. I think its frequency of use is probably less than iohexol. I haven't really researched that, and I don't have numbers to back that up, but I suspect that's the case.
All right. More general question here. Can this be used in any area of the country as long as it meets those basic criteria? So, west versus east, more arid versus a more wet climate, that kind of thing?
Yeah, you should be able to use this anywhere. At the end of the day, it just becomes it's just a modeling issue, and it's just understanding the modeling constraints that you're dealing with in your particular location. So it could be applied anywhere. We just happened to do a lot of this work in Florida because they had the interest in wanting to get this project going. It was sort of a unsolicited project where you had to have a certain amount of utility involvement, and there was a lot of interest in looking at something like this in Florida at the time. So that's why a lot of this work was done in Florida, but you could do this kind of work anywhere in the country. There's nothing specific to Florida in it.
Okay, good. Question here, if a community would like help with either testing or studying their discharges, or basically try to see if this application would work for them? Is that something that Stantec can help with?
Sure, absolutely. We have an alliance with Johns Hopkins University, and they have the ability to work with us to, they worked with us on these projects and helped us do all of this work. And yeah, if someone is, has the need and is interested in seeing if there's some applicability here, we'd be happy to talk to them about it and see if, that sort of application criteria is met.
All right, another question here. I'm asking about UV treatment. It's being adopted in a lot of wastewater facilities. How sustainable do you feel the choice of iohexol as a marker is going forward?
I think it's still pretty sustainable. I think that it's true that, there are more facilities interested in using UV, but there are also facilities that don't want to use UV. I think we're a long ways from having 100% wastewater utilities all working with UV disinfection systems. Some of these utilities are starting to become interested in peracetic acid as an alternative to chlorine. So I think it's, it's hard to really project out a trajectory and say, well, we're moving to the point where everyone's going to be on UV. I don't know that we can make a statement like that. And it's still possible that if you're in a very urbanized, very dense area and have very high loading, that you would still have enough in your effluent, even if you have a UV system. And then if we, ever get to the point where more work could be done on the degradates, it might be possible to find, a iohexol degradate that's really unique to that UV exposure. And that would be, really optimal, because then you would be able to track something that is only formed through that treatment process, and it would only be in that effluent. But it remains to be seen whether there really is any unique iohexol photolysis degradate in reuse effluent with UV treatment.
Okay. A question about future research, basically around how do you envision experiments around soil degradation? How would you advance the research from that standpoint?
I think we need a better understanding of what happens to the nutrients during that transport under different oxic conditions and different carbon accessibility conditions relative to what's happening with the iohexol. Because, what we were in the best worlds, if you were able to demonstrate that your degradation of iohexol never exceeded your degradation of the nutrients, it might be less important to really track that pathway in detail, because you could just say, well, when we travel through this pathway, yeah, we're losing some of our marker, but we're losing just as much or more of our contaminant we really are concerned about. That would be the best situation, because you might almost be able to ignore that transport pathway. But obviously what we don't really understand is the relative rates of dissipation of those two compounds with different soils, first off, and then with different oxic conditions. We did look at that in the second experiment, but we only looked at 2 soils, and we only ran, this column experiment one time. You know, we haven't gone through any vigorous replication. We haven't looked at a lot of other soils. And so I think that there's certainly not enough understanding of that to be able to build a model at this point.
Okay, yep, that makes sense. All right, kind of a broad question here, but let's talk about it anyways. Is there a prospect of using reclaimed water for domestic use as potable water? No, you've done a lot of research into reuse, obviously, Joan. I guess someone just wants to know your opinion on that.
Yeah, definitely. I'm located in California, and California is actively pursuing use of reclaimed water as potable water. There have been a number of pilot and demo facilities that have, looked exactly at that. And there are a number of studies going on looking at all of the support criteria, what kind of training programs would you need for your treatment operators, because now you have a facility that's basically going from wastewater all the way to potable water, and what are all the safety factors that you would have to build in, and how would you actually operate these facilities, and what would be all your contingency measures. So yeah, that's definitely moving forward.
Okay, great. I think we've got one more here. Let's see. Looks like it's I'm sorry for the leaf blower there coming in. Follow up on a previous question. What's the best way for utilities to estimate the potential biodegradation of iohexol in their area if they're interested in using that as a marker?
Okay, can you say that again? You sort of broke up, sorry.
So, what is the best way for utilities to estimate the potential biodegradation of iohexol in their area if they're interested in using iohexol as a marker?
Yeah. I mean, the best way is really to do soil column experiments. You could, if you just want to do something a little more preliminary, you could probably do some batch soil experiments. And then, you could control to get the oxic or anoxic conditions that you're looking for. Obviously, if, we're dealing with superficial aquifers, you're probably talking more about oxic conditions. If you're worried about impact to a very deep aquifer, you might be talking about a more anoxic condition. So you just could vary or control your conditions to try to estimate what you think is going on in the environment, and that would be the best way to start. And then just just monitor for the nutrients of concern and the iohexol.
All right. I am now going to let everyone unmute themselves if anyone would like to either comment or ask a question or provide an example of something similar. You're welcome to do that now. And if not, that's okay too. Just a reminder, you'll get a link from GoToWebinar with a recording for today. We also placed them on Stantec.com. And you saw in the chat there that we do have a calendar of upcoming webinars on our website as well.
Okay, I guess it was all clear.
I think so. I think you're off the hook. But thanks again, Joan. Much appreciated for taking the time and on this very interesting subject. And thanks for everybody that attended. Really appreciate it. And we hope to see you on a webinar in the future.
Thank you,
Have a good day, everyone.